This is Science in Parallel, a podcast about people and projects in computational science. I'm your host, Sarah Webb. In our last season, we focused on large language models and other types of foundation models for science. With this episode, we're starting our 7th season. We won't leave AI behind, but we'll focus on quantum computing, another growing and emerging area. As with AI, researchers are matching quantum algorithms with interesting scientific problems. Add to that a range of delicate and experimental hardware. In other words, this topic is right up our alley. Please subscribe on your favorite platform so that you don't miss any of our upcoming episodes. And share them with a friend or colleague. We hope you enjoy the new season. To launch this series, I'm speaking with Jarrod McClean, a senior staff research scientist in the Google Quantum Artificial Intelligence Laboratory. Jarrod completed his PhD in chemical physics at Harvard University, and he was a Department of Energy Computational Science Graduate Fellow from 2011 to 2015. This podcast is a media outreach project of that fellowship program. As the name of his workplace suggests, Jarrod thinks about this interface between AI and quantum computing, particularly algorithms and applications. Join us for a conversation about his work at Google, where he thinks quantum computing could soon enter the computational science workflow, and the mental gymnastics of harnessing hardware that researchers are still designing. Jarrod, it is great to have you on the podcast.
Yeah, great to be here.
So, I think where I'd like to start is for you to tell me about your job. What is it that you do? What kind of problems do you work on?
Yeah, so I'm a research scientist at Google, and I work on sort of the algorithms and applications of quantum computers to problems in machine learning and more broadly. We try to think about both foundational advances and more practical ones. We think about where we should take different research directions. We chat with other scientists. We chat both in academia and industry. And I personally might write coded prototypes. I might work on certain theoretical results. I might be writing papers or, putting together a plan for a new research direction.
So you talked about quantum machine learning. And so let's talk a little bit about Google and quantum computing and how some of these ideas that you work on fit there.
Yeah, absolutely. Google has broad goals in making quantum computers useful outside of just quantum science and technology. Really understanding what the landscape of that looks like. Say, if we had a quantum computer, what's its potential value to things Google cares about, to things humanity more broadly cares about? And of course, what is the risk in doing that? How challenging will it be to realize that goal? And I think there's a lot of maybe fundamental technology investments that Google does. Quantum may be among the more speculative, but I think it's one that we've gotten a little bit more excited about over time as we've hit more and more technological milestones. And I would say, of course, Google is very AI-centric at the moment, and we're hopeful that quantum computing can play some role in that. And if I had to sort of characterize my own role within, Google's goals, you could kind of think of a speculative technology effort as having at least two fundamental subparts. One is the risks of that. So, the costs of building it, the probability it will work out, and then the reward of, if it works out, what's the payout? And I feel like, as do the other people working on algorithms and applications, lean more in the rewards category of we try to figure out if our hardware team is successful, what's going to be the upside, both in terms of new kinds of computations or applications we can discover, and really value and impact to people's day-to-day lives. And if we can really boost that reward, it helps to build a foundation for diving more aggressively into riskier and riskier technology areas.
So talk about this idea of quantum AI. What does that look like? How is that different from what most people think about in terms of AI?
Yeah, that's a great question. I think we get this question a lot, in particular because it's in our group's name as well as one of our research interests. I think quantum AI for a lot of people has come to mean a pretty broad umbrella of intersections between quantum technology and, quantum computing and machine learning or artificial intelligence. And I've seen this kind of manifest in many different ways. For example, how will quantum computers impact the machine learning problems people are interested in today, assuming we, scale up our quantum computers and make them useful? It can also mean, how will quantum computers be useful in an analogous paradigm where data comes in a quantum form and we sort of process it directly on quantum computers? It has come now a little bit to mean, how will classical AI be empowered by quantum data? So this notion that data kind of makes different types of computation fundamentally more powerful. Once you've seen examples, it might be much easier to solve a problem had you not seen those examples. And we think quantum computers will probably play a role in supplying data to classical AI. And this will, even without running the quantum computer in tandem with the device, make it much more powerful. And so I would say there's many different facets in which now we imagine quantum will touch AI, and even including AI accelerating building the quantum computers themselves. And so we've lumped a lot of this into a similar family, and we spend time going down each of these somewhat distinct but related threads to try to figure out where the most viable pathways are.
Can you maybe walk through how that plays out in one of these examples, either accelerating or building systems, to kind of illustrate some of the things you were just talking about?
Yeah, let me maybe zoom in on two I find particularly exciting. So one direction from this that we are very excited about is this thing I mentioned about learning from quantum data, which takes a second to explain exactly what that is. So many people are, say, familiar with this illustration of Schrodinger's cat, where you have a cat that's sort of both alive and dead before you open the box, and then you open it and it kind of collapses into one or the other. This bears some resemblance to the way we do experiments in many physics labs today. We prepare some system that we're interested in studying, manipulate it a bit, and then we do a measurement and read, say, a classical number out. And this is like the cat being alive or dead. We repeat it many times, and this string of classical data for us sort of comes in and we analyze it. So something we realized recently is that if you have a little more control over that, say you have a quantum system, its ability to manipulate that cat in the alive and dead state before you collapse it into one or the other can help you reveal far more information about that physical system than if you're forced to collapse it first. And really, the ability to do that manipulation is very much what quantum computing is trying to achieve, that we can manipulate these coherent parts of our universe without collapsing it first. So what we found, kind of roughly speaking, is if we take sort of two copies of that Schrodinger cat and use a quantum computer to look at it, even with kind of a simple scheme, that ability to manipulate things quantumly lets us learn about that, say, cat system exponentially faster than we would be able to do without this kind of technology. And so what that means is there are systems for which it might take longer than the age of the universe to measure this quantity about the system. So granted, it's only in somewhat specific cases we've proven this for so far, and we're trying to push it closer to, like, say, real world applications. But that's one vein I think we're very excited about. There's a few missing pieces of the technological stack we'll need to really make that work. So more sophisticated quantum sensors and a technology called transduction that moves it from the sensor into the quantum computer, and all of these pieces of the pipeline need to work well enough. But I think we're very excited about that general direction. Another one that's really exciting to kind of point out that's maybe a bit more near term is the one I mentioned about empowering classical AI today with data from quantum computers. So there's a few problems, say, that one, like many people in the computational science world, I think are pretty interested in, like simulation of chemical and material systems. This could include, catalysis with rough surfaces. It could include, strongly correlated biometallic enzymes. And you want to do these simulations and learn something about them, and from that make design choices. So a lot of these we think are quite challenging to do when the systems become strongly correlated or for certain particular reaction types. But we think quantum computers would be very good at these simulations. And this behavior, because it's in a physical system, is somewhat regular. So we've started to ask the question, started in part by this power of data paper that we worked on, where we showed there were problems that even when they were hard with just a classical computer and easy with a quantum computer, they actually also became easy when the quantum computer passed some amount of data to the classical computer.
That paper was published in Nature Communications, and there's a link to it in our show notes.
You can imagine that I go and do my chemistry or physics simulations. I watch the atoms and molecules move around, record a bunch of data from my quantum computer. Now I turn my quantum computer off, but I have that classical database that future classical computers get to use. And now they can solve a wider set of problems than they could without that database. And so that allows us a much more near term, and I would say widespread application of quantum computers that comes from the ability to empower AI or general classical simulation methods with data from quantum computers. And I think those are two avenues we're very excited about.
Let's expand out a little bit to sort of talk about, hey, if we have these ideal quantum computers doing what we want them to do, what kinds of problems could we start to think about that were, difficult or impossible for us to do previously?
Yeah, that's a great question. And I think there's a lot of interesting things to say about that, especially with analogy to how we saw AI develop in the last few decades. And so maybe a way to start talking about that is to talk about at least a little bit of the progress we've seen experimentally. We're very interested in achieving experimental demonstration of quantum advantage on useful problems that are where I'm kind of defining useful to mean people outside of quantum computing would care about the solution, whether or not it came from a quantum computer. And so we've been stepping progress along for that. We have had for many years small systems of noisy qubits that have grown and they've improved in quality. And because of the noise, it's often been hard to do simulations that surpass what we could do without quantum computers. And in recent years, that's changed a bit. So we have demonstrations we believe are beyond the capabilities of classical computers, but they're not easy to directly verify. So these are sort of these random circuit sampling experiments where you can kind of infer that you've entered the beyond classical regime, but that's not quite as satisfying as you'd like it to be. More recently, we did a demonstration of a quantumly verifiable advantage, meaning if you and I both had quantum computers, we could both run the same problem. And if we believed in our own result, we could sort of check that your result was consistent with that. And that's like a little bit further. But the gold standard is sort of, at least for early demonstrations, classically verifiable advantage. So some problem that's easy to verify, but hard to compute. So you can challenge me with the problem. I use my quantum computer to solve it, send you the answer, and you can say, wow, yes, they did it. And the prototypical example of this is, of course, factoring large numbers with applications to breaking cryptography and general study of kind of number theory and things like that. So that, last one we can't do yet. And there's a lot of proposals for how to move the needle forward on that. There's always been an up and down interest in general optimization problems. So can quantum computers find you the design variables that you want to have to optimize some, maybe minimize wind resistance or do something like that? And I think people have oscillated over time how impactful or how good quantum computers will be at this problem. I mentioned factoring. It can have implications for breaking cryptography, or perhaps if you wanted to view it in a more positive light, for pushing us towards better security across all of our systems that won't be vulnerable to these types of attacks. And it can also be for other types of learning and sensing that I mentioned before. We're kind of hopeful that it'll impact machine learning and AI in both this kind of quantum data regime as well as classical one. The hardware has sort of moved much faster than I might have expected, and algorithmic improvements have stacked on top of that. And so I feel like I would not be surprised if we entered at least this regime of sort of beyond classical computations that are classically verifiable for maybe something like a number theory type problem or early quantum simulation by something like 2030, which if you had asked me 5 years ago, I would have said much longer than that.
What are the big challenges that you're thinking about right now in this work?
So I think a lot about the intersection of how is quantum going to influence how we do machine learning and, of course, how we learn about quantum systems. And I think maybe there's a few things worth highlighting in this space. One is this maybe analogy to how AI progressed classically. So if we kind of go a little bit back in time to maybe the 70s or so, there were a lot of the foundational ideas appearing that are used in modern AI systems, neurons, multi-layer perceptrons, and things like that. But computational power and data availability was a bit limited. And so people tried to bridge the gap a bit with development of learning theory to get a better understanding of what systems we could expect to learn, when could we expect AI to succeed, when was it kind of a fruitless endeavor. And I would say we're in a somewhat similar situation now with quantum computers. We don't have the scale or large enough robust quantum systems to go out and do the same data sets as people do classically today. And so a lot of what we have to do to make progress is work on these systems with pencil and paper. But that kind of restricts us a bit to what we can sort of rigorously show is true. But it's really hard to say rigorously define what a real world data set looks like. And this seems to impact learning quite a bit. So if we take a step back on that analogy that I mentioned to classical learning theory in, say, the 70s, people worked on this theory of, say, pack learning, which is still, of course, used today and used in quantum, which is probably approximately correct learning, PAC. And what they found was that for a lot of problems, they would conclude in the worst case, they were unlearnable. So you started to see problem after problem where if you read into this too seriously, then, we couldn't learn anything. But luckily, that didn't discourage everyone. At least some people plowed forward and continued to build these systems further and further along. And now we see, of course, incredible effectiveness in AI and tasks like image recognition, text generation, even coding now, all things that if you'd really listened too closely to your pencil and paper results, you might not have even attempted. And I hope we don't get too much into that situation with quantum computing when the way we develop applications right now is we do try to do a lot of pencil and paper proofs and compare it to similar scaling analysis that we do classically. And I think it's nice that we have some problems where we suspect there's going to be a robust separation that quantum can do well on. But I think we shouldn't be too discouraged before we can at least do some of the same empirical explorations that we've done classically, which are required to see really the capabilities of these systems. And so I work a little bit on both the pencil and paper aspect of that because you have to do with what you can with the tools you have. But I also try to prepare for the times of, say, early fault tolerance, as we call it, so early error corrected quantum computers and just beyond that, so that we can enable the empirical explorations we might need to get to larger data sets and see emergent phenomenon where quantum is doing much better than we might have predicted by pencil and paper. Maybe we don't understand yet why, but we can still use that tool effectively.
That seems really exciting to think about. I mean, it's a little almost science fiction to me to be thinking about, okay, what I might be able to do with a system I don't have yet. Do you ever open your email and hear from a colleague and go, oh my gosh, I can suddenly do something I couldn't do yesterday or last week or last month?
Yeah, I feel like we have had a lot of that push and pull over the years. So things have sort of shifted in the field a bit these days in terms of belief of what the best pathways are to reaching useful applications. Not too long ago, I was thinking about how do you make the devices we have right now get as close to this quantum and classical boundary as possible. And so there really would be a back and forth day to day of, oh, these gate fidelities got better, these qubit lifetimes got longer. And I think some of the work I've had that's had the most impact or taken off has been things really inspired by the true constraints you have in order to try to run something. I would say more recently, after many years of trying this for smaller size systems, people have started to think, well, maybe we do really need error correction for this to work. And so a lot of our metrics have become more driven by how they impact our error correction success. And a lot of our architectural designs are similarly impacted. But I think in that domain, we now and previously have a much more aggressive back and forth of someone prototypes a new error correcting code they might think has better properties, but it's, say, missing some component or aspect of the device that would really let it happen. And so then there's a back and forth of, can we make this possible? I don't think so, move on to another code. But then maybe a month or two later, they come back and say, I thought about it some more, and I think we can do that. So maybe this is a space we should go into. And rapid developments like that between the hardware team and sort of error correction can really change the trajectory of what I, an algorithm designer, might expect to have in 2, 4, 6 years in terms of not just raw physical qubits on the device, but early logical qubits and protected operations. And so it impacts the budget of, as we go out and say, what are some of the first computations we're going to run? How do we think about how to use that budget most effectively? And, that will even change day to day at that abstract level of, I think we'll have 10,000 logical qubits with a million operations. And maybe a few weeks later, they'll say, actually, maybe it could be 100,000 by that date. So it's a very fluid space. And we try to adapt to the resources we think we'll have and get the most out of them, once again, by pencil and paper, which is a bit of a strange way to develop for anyone listening who's probably done a lot of computational science. Like, you might even ask, how do you know your programs are going to compile or be correct if you've never actually run them? Which is a fair question. We're going to have to work that out.
Logical qubits group together multiple physical qubits made from superconducting circuits, trapped ions, or other technologies. Logical qubits help to manage unique challenges in these systems, allowing them to store information long enough for computation to be completed. Quantum systems are fragile, and jostling in the environment can change their physical states and make them lose information. Quantum error correction strategies rely on spreading information out over multiple qubits. How many physical qubits are within a logical qubit remains an open and evolving question. The answer depends on many factors, including whether researchers are using superconducting qubits, like Google does, or other platforms. Jarrod discussed this in detail, and we'll share that as a bonus mini episode. But here I wanted to get a rough idea of how large quantum systems need to be to do useful computations, at least right now. One of the things that I'm, trying to imagine in this space is exactly what, as quantum computers emerge and become practical devices, what are they going to look like? I mean, are they going to be freestanding quantum computers that go off and do their quantum thing and then you take an output and use it? Are they going to be linked in as a part of supercomputers, HPC systems? Obviously, people are working on all of those things. As someone working in the field, how do you see things evolving in terms of what the first practical systems might look like?
Yeah, that's a great question. It's going to be interesting to see how these devices emerge and what roles they play in the near, mid, and long term. And I think we're seeing bets by different companies and academic groups on them emerging in basically any form we could have conceived by analogy to how we do computing today. So, of course, it's easiest to build these because they often require somewhat bespoke and custom equipment to maintain control systems, cryogenics, etc. It's easy to kind of have everything in-house and have it kind of be all parts of a research process with, different connections. And so that makes it tempting to say I'm only going to keep them in-house. And maybe that mimics very closely how we see cloud architectures today, where maintaining a complicated or large or often changing system, it makes more sense to have the people who built it always next to it and modifying it, and then users can log in and use it. So I'd say cloud model access is via sort of classical controls where you submit programs, run them, and get some results out, has been the most popular way they've been deployed, say, outside the groups that build them. I think other groups have indeed sold devices that then sit on, say, the property, kind of like the Department of Energy does with supercomputing centers, where you might have facilities set up to house someone else's device. And we've certainly seen some of that so far. We've seen people investing in quantum networking, meaning instead of just taking classical program specifications, I want to be able to link two distant quantum computers with something that is also quantum that nominally kind of creates one larger quantum computer or creates opportunity for communication type problems. And so we've seen all of these coming out sort of at the same time, probably in part because we have some experience in what's been successful classically, and we think that maybe quantum will repeat that success in a way. But I think we're really going to have to wait a bit to see how people start using them for their real applications to know what the dominant architectures will be. And perhaps it will be a mix of all of these. I personally think there has to be benefits to these kind of quantum communication type applications, even though they're harder to implement with certain architectures. But in certain ways, the internet, we didn't really predict the way it would take off, but fundamentally just connecting people and connecting technology seems to pay long-term dividends. So I'm hopeful that that's going to be an area where there's a lot of success. I think in the near term, the challenge of maintaining these expert systems means they will predominantly live in the places they're developed and be connected to remotely and classically. But I think we could see that shift quickly if, for example, someone found an application that was very clear and very valuable, but required two distant networked quantum computers. That would add a lot of fuel to the fire to push in that direction, because I don't think there's anything preventing that. We're more guided by the guiding star of where is there likely to be the biggest application impact and value, and let's shoot for that first and worry about the other possibilities later. But that could all shift overnight because, you never know what people are going to invent tomorrow, I suppose.
Is there anything else that you're particularly excited about in this space that you think is important to let people know about?
I guess maybe one thing I'll say along the lines of the speculative direction that maybe we need the technology to know what it's good for. I don't think we would build the technology if we didn't have a few good ideas of what it might be good for, but I'm excited to be open to the possibility of things that we have not anticipated yet. So, of course, I think there are some often repeated quotes from the inventor of the laser that I don't know how true they are, but they often say, this is a toy. I have no idea what this will be useful for. And yet here we are some decades later, and lasers are everywhere. They're an incredibly useful tool. It was very hard to predict what their utility would have been. I feel like quantum has to sort of sit in this realm for maybe a very basic or naive reason, which is it's clear to us now after many decades of experimental science, the universe is sort of fundamentally quantum. And if we want to continue to interact with it at deeper and deeper levels, have finer and finer control and build more and more technology, then our ability to manipulate things at a quantum level has to be a crucial part of this. And the practice of building a quantum computer is the practice of gaining finer and finer control over the quantum aspects of our universe. And I just feel to my core that this is going to unlock things we couldn't have predicted in our ability to sort of manipulate the physical world. We view quantum computing right now very much through the lens of what we've used classical computers for, but I think there's going to be so much more. And I'm excited to get there. If I knew exactly what it was, I would tell you, but maybe that's part of the fun.
If you were sitting in a room with early career researchers right now, either computational scientists more broadly or people interested in quantum computing, what piece of advice would you want to pass along?
Yeah, I guess maybe this would follow my own career trajectory a bit, but I would also advise them, because quantum computing is a speculative but exciting area, and it's one where things are changing all the time overnight. And so I think it's worth it to, stay curious and be flexible in the topics you work on, the directions you feel like you could take. And, it's sometimes tough to predict, I think, what work you do that will take off. So the best you can do is to kind of do good work on any topic that you're interested in, and definitely put an effort out in sharing the work that you do. I think I heard it once said that the recipe for success is simple, but crucial to do both parts of it, which is do cool stuff and tell people about it. Without either side of that, it doesn't work. But yeah, it's a simple recipe, I guess. And maybe as more targeted advice these days for young computational scientists or people entering the field that's not quantum specific is, I don't think I've ever, this is diving a little bit away from quantum into AI. I don't think I've been alive where I've seen more rapid progress than I have in the last 6 to 12 months in the way AI tools interact with not only how people play with them as toys, but they're now entering serious researchers' pipelines in a big way. And people who are using these tools are becoming 10 or 100 times more productive. And I think if you want to succeed, these tools have limitations, but they're evolving all the time. You need to understand what their trajectory is and how that's going to impact your future in both kind of career-wise, research-wise, and, general life. I think these are coming in a big way. They're entering our quantum research pipelines. We're often thinking about how they're going to impact mathematical proofs, program development, how quantum's going to feed back into that. And I don't know, I've never seen anything move so quickly, and I've never been so blown away. So stay on top of that if you're young in your career, especially.
Jarrod, thank you so much for taking the time to tell me about all the cool stuff.
Absolutely. Thanks for having me.
To learn more about Jarrod McClean and his research, additional information about superconducting qubits, and Google's Quantum AI Laboratory, check out our show notes at scienceinparallel.org. Science in Parallel is produced by the Krell Institute and is a media project of the Department of Energy Computational Science Graduate Fellowship Program. Any opinions expressed are those of the speaker and not those of their employers, the Krell Institute, or the U.S. Department of Energy. Our music is by Steve O'Reilly. This episode was written and produced by Sarah Webb and edited by Susan Vallet.